Hi, and welcome again to this physics review session. So for this session, we will be reviewing about the most common second-order differential equations that we usually encounter in physics, and this is the harmonic oscillator differential equation. So let's start. So what does a harmonic oscillator second-order differential equation looks like? So it's basically just Hooke's law. So if you recall Hooke's law, F is equal to kx. So the force here is basically a second order differentiation in position with respect to time multiplied by mass. So m times a, mass times acceleration, and it's equal to k x. So you obtain this familiar type of differential equation, k over m x. Okay, so Hooke's law is one of those types of harmonic oscillator equations. So it's a simple harmonic motion equation. But say let's generalize this, because we will encounter similar types of equations. So you say you have d squared y dx squared is equal to plus and minus k squared y. Okay, this one. So the solutions will be different if you take the positive sign, and it will be different if you take the negative sign. Actually, if you take the positive sign, the solutions will be hyperbolic function, but still oscillating functions. And if you take the negative sign, negative k squared y, then the solutions of that are sinusoidal functions, but still oscillating equations. So the solutions to this are oscillating functions, hyperbolic cosine and hyperbolic sine, hyperbolic sine and hyperbolic and sinusoidal functions rather. Okay, so how do we evaluate this? How do we achieve with the general solution for this? Okay, so first let's convert the second order differential equation, second order operation here into something much more simpler. So this second derivative of y with respect to x is actually just the derivative with respect to x of the first derivative of y with respect to x, right? The derivative of the first derivative, that's basically the second derivative. Now, if I want to change my differentiation, say from d dx, I want to change it to d dy, what should I do? So I just get the derivative of y with respect to x, and then I can now change to d dy, dy dx, right? So if you look at it, dy here will just basically cancel out dy and dy, and you get d dx, right? Okay. Now, if I multiply this by 2, so I will get a 1/2 factor, and then I will have 2 dy dx d dy of dy dx. I'll just multiply by 2 and 1/2. Now, if you will notice, this term here is basically the derivative with respect to y of dy dx squared. So can you check it? So if you take the derivative with respect to y of dy dx, then you have 2 dy dx, then the derivative with respect to y of dy dx. So you get essentially this one. So therefore, the second order differential equation, or this operation, or this operator, is essentially equal to that one. Okay, so we now have this equation here, d dy, or sorry, it's 1/2. So the second order differential equation is basically uh, 1/2 this one, d dy of dy dx squared. So that one. So the second order differential operator is basically 1/2 d dy dx squared. Okay. So we have 1/2 d dy dx squared is equal to plus and minus k squared y. So this will now be an equation easier to solve. So how do you first solve this equation? So first, we cross multiply 2 and dy, and you will have on the right side, you will be left with, left side rather, d dy, sorry, you already cross multiply dy or multiply dy both sides of the equation. So what's left with will be the differential of dy dx squared is equal to plus and minus, there will be a 2 factor, I cross multiply 2, then k squared dy, k squared y dy, k squared y dy. Now I'm gonna do is I'm gonna integrate this. So indefinite integral first. I will just add some constants later. So the integral of the differential of this is basically just this, right? So you will be left with dy dx squared, and integral of y dy is y squared over 2. So there's a 2 here, so cancel out. So you have 2, cancel out. So you're left with k squared y squared. Okay, so these are all squared, so we take the square root. So the square root of dy dx squared will just be dy dx. So we will have the square root of plus and minus 1. We will deal with that later. And the square root of k squared and y squared will just be essentially plus and minus ky. So I have a plus and minus square root of plus and minus 1 ky. Take note, the square root of something is always plus and minus. So the square root of x squared is plus and minus x. So plus and minus, and then the square root of each of these term here. Okay. So we cross multiply y, so we will have dy over y is equal to plus and minus square root of plus and minus 1 k dx. Okay. So and then integrate again. So integrate. So integrating, so you will get, say, ln of y is equal to the plus and minus square root of plus and minus 1 of kx, and we'll just add here some integration constant, say plus c. Okay. So I can actually let my integration constant as, say, some ln of a, so that when I combine it with here, when I transpose this integration constant here, I will have ln of y minus ln of a, which is just ln of y minus a. So essentially I will have my equation will now look like something like this. So I'm just going to erase this. So I will have something like ln of y over a. So I combine these two constant, these two ln's here, and it's equal to plus and minus square root of plus and minus 1 kx. So if I convert this into an exponential form, so I have y is equal to a e to the plus and minus square root of plus and minus 1 kx. Okay, so this means that if we take the positive sign earlier, uh, of course this is always plus and minus. So the solutions could be a e to the plus and minus. If we take the positive sign, then square root of positive 1 is just 1, so plus and minus kx. If the differential equation looks like this, d squared y dx squared is equal to positive k squared y. But uh, this is actually equivalent to a e to the plus and minus if we take the negative sign, or if your differential equation was negative k squared y instead of positive k squared y, then you take the lower sign. So the square root of negative 1, that's I. So you will have I k x. So these are the two solutions. Now you can actually combine e to the kx plus e to the negative kx over 2 to get hyperbolic cosine kx. So you can combine the e to the kx and e to the negative kx solutions to form hyperbolic cosines. And in this case, you can also combine e to the ikx plus e to the negative ikx over 2 to get, say, cosine kx. So your solutions now can be in terms of exponential, or it can be in terms of sinusoidal functions. Okay, so utilizing this, we can now generalize our results. So if your differential equation d squared y dx, or harmonic oscillator equation, has a positive k squared y, then the solutions to this will be y is equal to a combination of the exponential, two solutions, e to the kx and e to the negative kx. So you have a e to the kx plus b e to the negative kx. Take note, we are using the linear algebra property here of solutions. So if e to the kx is a solution and e to the negative kx is also a solution, then any combination of them is also a solution. So since we can combine e to the kx and e to the negative kx to form hyperbolic cosine, then say c hyperbolic cosine kx plus d hyperbolic sine kx is also a solution. Okay, sorry, I'm just gonna put it here, plus d sinh kx. So these are the two solutions if your equation, or if your harmonic oscillator equation is equal to positive k squared y. Now, if you have the negative k squared y, so if your harmonic oscillator is like equations like this, negative k squared y, then of course the solution to that will be e to the ikx. So if e to the positive ikx is a solution, and e to the negative ikx is also a solution, then any combination of them will also be a solution. So e to the positive ikx plus b e to the negative ikx. So if e to the ikx is a solution and e to the negative ikx is also a solution, because there are two solutions here, plus and minus ikx, then any combination of them is also a solution. And since based on this formula here, you can convert the combinations of e to the ikx and e to the negative ikx to cosine and sine, then you can also write this solution as c cosine kx plus d sine kx. So these are now your two solutions to choose from if you have a differential equation like this. Similarly, for this differential equation, you also have these two solutions, hyperbolic function solution. So that's it. That is how we solve the harmonic oscillator differential equation. Okay, so that's the end of this review session, and I will see you again in the next review session.